So hi everyone, my name is Roshan. I'm a student at Carnegie Mellon University, and I'm going to be talking about structured output learning for this task of joint ASR and diarization. So first of all, thanks to the whole end-to-end ASR sub-team at JSALT who helped me develop this through the workshop. So first I'd want to set up where exactly this project falls in the space of work that we've seen today. So when we look at long multi-speaker recordings, there are many pipeline systems. These pipeline systems have different stages. Often it's just speech separation followed by speech recognition on each speaker stream separately, and then the results are put together. There's another system which is based on target speaker ASR. So there, the difference is that enrollment audio and embeddings are used to drive the speech recognition to focus on a particular speaker. Then we have this other class of methods which are modular but still use end-to-end training. So this was talked about by Wang Yu particularly. So you have these modules of speech separation and recognition, um, and it's trained completely end-to-end. So then comes this work, which basically does joint speech recognition and diarization using a single non-modular network. So the idea here is to be able to transcribe meetings with both speaker information and the transcript. So the differences between this work and the other work that's been talked about today is one is this work uses a form of cross-speaker lexical context. That is, if you're processing conversations real time, this could be really helpful in speech recognition, and it's been shown in different works. So it has a non-modular structure, which makes it an elegant architecture, but also makes it slightly challenging to interpret since there are no clear intermediate outputs. This work also does implicit speaker diarization, which means that we produce the speaker IDs as tokens on a closed set of speakers. And to deal with open speaker sets that we've not seen during training, we propose speaker embeddings and clustering. So let me get to it. What is it exactly that we're talking about? So when we look at end-to-end ASR for long meetings, there are three things that are very important. One is dealing with long range of audio recordings because ASR models are typically trained at utterance level. So we need to extend that. Then the other part is looking at multiple speakers. Again, typical ASRs are trained at utterance level, which means one speaker says an utterance. But here we want to be able to process multiple speakers. The third thing is overlapping speech. So in order to deal with these, we are inspired by these two works in particular. So one is a work by Google, which talks about uh, multi-speaker modeling and long-range modeling in the context of doctor-patient conversations for conversational ASR. So they introduce speaker role tokens. Um, the other idea that we're inspired by is by Naoyuki Kanda from Microsoft. He gave one of our talks. So the idea here is how to deal with multiple speakers and how to deal with overlapping speech. So here they deal with overlapping speech based on first in, first out transcript serialization, which I'll explain a bit more in a bit. Oops.
Can you control it? I actually
It looks
just
like it's frozen for some reason.
just use okay.
Okay. I think it's working now. Let's see. Yeah. Okay. Thanks. So the idea here is structured output learning. So the ultimate goal is to learn who speaks what and when. And the idea is we have this long form meeting audio and we have a transcript of the form which is shown in the bottom right. So we have speaker ID, we have start time, we have whatever the transcript is, and then we have the end time for that particular speaker, followed by what the next speaker is saying. So even if it is overlapped speech, the transcript is serialized based on which speaker speaks first. Um, and the other component of this is, well, this is fine if you have a closed speaker set and you know all the speaker IDs. For an open speaker set, what you would do is we'd use speaker embeddings and we'd learn clustering algorithms over them to help with that. So these are, sorry. Yeah, so these are the evaluation metrics that we'll need to be looking at. So we're doing speech recognition, so WER, speaker ID, so we look at speaker ID accuracy, and on open set, we look at clustering metrics like purity, homogeneity, completeness. And we'll also look at how well the model can learn structure through structure prediction accuracy. So this is an overview of sort of our experiments. So in this talk, I'll be talking only about the work for ASR and speaker ID. There are extensions to diarization, which is ongoing work. So in this scenario, let's consider single speaker recordings. That was our first test to see if this idea works. So we worked with LibriSpeech 360 hours of clean data and switchboard, but I'll be discussing only LibriSpeech with time, due to time constraints. So we have a transformer model which we use for ASR. There's no language model, and the validation set contains the same speakers as the training set, which means we can compute speaker ID accuracy in the validation set, which is important. So these are two examples from the outputs. So in the first one, the speaker is recognized correctly, which is highlighted in yellow. The second example, which is in orange, the speaker isn't identified correctly. So the output looks like this. So speaker ID followed by text transcript. So these are some results from the ASR perspective on word error rates. So the baseline model achieves 7.2 and 7.5 on dev clean and test clean. And the proposed model improves on them slightly, 6.9 and 6.7. This merits a bit more investigation in the sense that we want to see if predicting the speaker ID helps, for example, constrain the beam elements during decoding to something that is more relevant and therefore achieves better performance. The other thing of note to point out is that over the validation set, when we score with and without speaker labels, the difference in WER is negligible, which is also an indicator that our prediction of the speaker IDs is pretty good. So looking at how well this model learns structure, that is the structure that we have said is first it'll predict the speaker token followed by the text transcript. So we are measuring that with structure prediction accuracy. Does it get the speaker token right? And it appears that in most of the cases, it does get the speaker structure right, which is great. So the next thing is speaker identification. So on speaker ID, we get 90.6 accuracy on the validation set, which is reasonably high, and it's good. So the next thing that we're looking at is, okay, this works in the closed speaker set scenario. What about open speaker sets? So here we come up with the idea of implicit speaker representations. So we contend that even though this model has no explicit speaker embedding during training, there are some implicit model parameters that could be considered as speaker representations, and therefore we can apply clustering on them. So one of these is the logits, so-called logits vector, which is the classification output prior to the softmax used in the ASR. And the other one is pre-logits, which is another hidden state vector before the projection to classification. And we use these representations and carry out k-means clustering, and we have some results on that. So on clustering, we have three measures: purity, homogeneity, completeness. Homogeneity and completeness are sort of a measure of cluster consistency. And what they really mean is if there are data points within a cluster, do they map to the same speaker? And do all the points of a given test speaker, are they all clustered in the same cluster? So that's what homogeneity and completeness measure. So for the logits vectors and the pre-logits vectors, without normalization, we get not so good scores. But when we take from the logits only the elements corresponding to the speaker tokens and then normalize them using softmax, we seem to get reasonable results on purity, homogeneity, and clustering, and those are the best results marked in bold in the table. We also try to perform this analysis based on just predicting the speaker token, and that purity is slightly lower. So this gives us hope that yes, speaker embeddings do work to some extent, and it is possible to find better speaker embeddings. So the other part I wanted to discuss briefly is how does this work with multi-speaker meeting recordings in this LibriCSS setup. So we train on simulated LibriSpeech with RIRs, with reverb and noise, with up to 30% overlap, one or two speakers, the same ESPNet model and no language model. So here we have some initial results on WER. So this number is 21.9 WER, I think the baselines without language model are at around 19. Um, so the main reason or the main issue in this model currently is that we are not able to deal with overlapping speech very well. You can see the example below. So this is an example from the simulated test set, which has two speakers. The second speaker is partially interjecting into the first utterance, which is why you just see one word farewell from the second speaker. So if you look at sorry, I think hypothesis and reference are switched. But yeah, so if you look at the second one is the hypothesis. So if you look at the hypothesis, there's a substitution error with brothels, and then it doesn't predict the second speaker part. So this may be because the data set we're dealing with has very low overlaps. So another task to look at is how about we introduce more overlaps in the data and see how the model performs. So we also found speaker counting accuracy on the set, which is 82.33, which is considerably high. But this number must be tempered by the realization that most of the test set is actually single speaker, and there's a few instances of two speakers. So it's a good start, but yeah, we have places to go. Um, Finally, I'd just like to conclude with some takeaways. So structured learning works well, as we proved. The accuracy is very high, above 99%. Then who speaks what, which was the idea of this work, seems to work well with a closed speaker set. We have seen that through validation accuracies. The non-modular approach works well for single speaker recordings and small overlap recordings. The implicit speaker recordings work reasonably, but of course there's room for improvement, which is why one of the tasks I'm working on is explicit speaker embeddings using maybe target speaker methods, multitask methods, and so on. I'm also looking at advanced clustering techniques because, as I mentioned, I just use k-means. Another thing is to look at dealing with large overlaps. And finally, there's the idea of jumping from ASR plus speaker ID to ASR plus diarization, introducing timestamps. So that's it from me. In case anyone has questions, you can email me later or ask me in the chat. Thank you.
Thank you, Roshan. I actually think I see some. Can you stop the remote control?
Oh yeah, sorry.
Yeah, I think in the chat. Is there a question in the chat?
No questions on this one.
Okay.
In the Q&A or the chat.
I see. Okay. Feel free to ask questions for the Q&A. And if not, I mean, we will let Shinji to conclude our presentation, and we will end our final presentation. It's a pretty long one. Thanks again for the listening.
Okay, so I just would like to first thank everyone in the presenter, participant, organizer for this great presentation and discussion. We actually had a difficulty of this workshop due to the COVID-19. However, with a lot of help and way to establish the collaboration due to the regular meetings, Slack, GitHub, email, and so on, we finally got the great outcomes. For example, this meeting scenario has been studied for a long time in the community. And at that time, we didn't have a way to solve it. However, all of our methods are promising, or some of them we can say that solve this kind of problem. So I'm very excited about it. So this workshop, way to collaborate even in the remote workshop and great outcome would be a good example for the community, I believe. So finally, I'd like to thank again for the team members, participants, organizers, including Sanjeev, Najim, Yendar, and also our kind of a group leader, Joe Chen. He showed a strong leadership management in addition to his research activities during the workshop. Thank you very much.
Thank you.
Well said, Shinji. Thank you, Zoe. That was a tough one. It was more than we ask of team leaders. You had to lead a remote team this year, and you pulled it off very well. Thank you. Thank you very much. Okay.
Thank you.
Right. So thank you also to the audience for persisting through this long presentation. If you have any more questions, there are lots of ways to follow up. And as you saw when you signed up for the webinar, the team is planning to continue some meetings. And if you indicated yes, we will put you on our list when we have these meetings, and you can continue to engage with them. So with that, let me end, and we will see you tomorrow morning at 9 o'clock sharp for the second team's presentation. Right? Thanks. Bye, everyone.
Bye.
Bye.